Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of mid-20th century physics was one of profound dualities, a world often partitioned between the pristine realm of analytically solvable linear systems and the vast, intractable wilderness of nonlinear phenomena. It is within this context that the research program led by Martin David Kruskal at the Princeton Plasma Physics Laboratory commenced, culminating in a 1965 publication, with Norman Zabusky, that represents far more than a simple discovery. The work surrounding the Korteweg-de equation during this period presented a fundamental reorientation of scientific inquiry, demonstrating that computation could serve as a tool for profound conceptual revelation. This essay will undertake a direct and systematic evaluation of the core claims advanced within this pivotal body of research, primarily, as articulated in the landmark 1965 paper, interaction of solitons in a collisionless plasma and the recurrence of initial states. We will proceed section by section through the implicit and explicit arguments of the work, analyzing its methodological assertions, its observational claims regarding emergent phenomena, its revolutionary conceptual framing, and its proposed resolution to one of physics' great contemporary paradoxes. The analysis will focus with surgical precision on the internal logic, evidence, and intellectual architecture of the work itself, assessing the validity and impact of its propositions as they were originally presented to a deeply engaged and initially perplexed scientific community. Section 1. The revitalization of the Korteweg-de equation. The foundational claim of the Kruskal-Zabusky research program is an act of deliberate scholarly exhumation. The work begins by positing the relevance of a particular 19th century partial differential equation, formulated by Diederik Korteweg and Gustav de Vries 1895 to describe shallow water waves. At the time of Kruskal's investigation, the Korteweg-de, or KdV, equation occupied a specialized and somewhat antique corner of fluid dynamics. The initial argument presented is that this equation, represented in its normalized form as the partial derivative of a function u with respect to time, plus the function u multiplied by its partial derivative with respect to a spatial variable x, plus the dispersion parameter delta squared multiplied by the third partial derivative of u with respect to x, all summing to 0, serves as an excellent continuum model for a wide class of physical systems exhibiting both weak nonlinearity and weak dispersion. This initial claim is a crucial intellectual bridge. It proposes that the complex, discrete dynamics of a one-dimensional lattice of masses connected by nonlinear springs, a system of intense interest following the Fermi-Pastor-Ulam-Singu experiments, could be faithfully captured by this specific, continuous partial differential equation. The evidence for this claim, within the paper's introductory framework, is largely theoretical. It relies on an asymptotic analysis, asserting that in a particular limit of long wavelengths the KdV equation emerges as the governing dynamic. The evaluation of this claim hinges on the validity of that limiting process. Contemporary and subsequent analysis affirmed the mathematical soundness of this derivation. The work's power, therefore, begins with a carefully reasoned argument for the utility of an old tool in a new and perplexing context. It repositions the KdV equation from a historical curiosity into a potent instrument for investigating the mysterious lack of thermalization or energy equipartition observed in the Fermi-Pastor-Ulam-Singu numerical experiments. This selection of the KdV equation was a hypothesis in itself that the key to the F-Boot paradox lay within the specific interplay of nonlinearity, represented by the term showing the function u times its spatial derivative, and dispersion, represented by the third derivative term. The work's preface effectively argues that this equation is the simplest mathematical stage upon which this crucial physical drama could be observed. Section 2. the computational experiment as a methodological claim, the second major claim advanced by the work is methodological. Having established the KDV equation as the object of study, Kruskal and Zabusky proposed to investigate its long-time behavior through direct numerical simulation on a digital computer. In the early 1960s, this was a significant proposition. The dominant culture in theoretical physics and applied mathematics prioritized the search for exact, analytical solutions. Numerical work was often viewed as a form of approximation, a tool for engineering problems, lacking the fundamental insight of pure theory. The paper implicitly claims that a carefully constructed computational experiment can function as a platform for discovery capable of revealing deep structural truths about a mathematical system that were inaccessible to prevailing analytical techniques. The methodology itself is detailed with a physicist's practicality. They implemented a finite difference scheme to solve the KDV equation on a periodic domain, meaning the system was treated as a closed loop. The initial condition was a simple, smooth cosine wave. The evaluation of this methodological claim rests on the fidelity of their numerical scheme. They had to demonstrate that the phenomena they observed were genuine properties of the KDV equation and were artifacts of their computational method, such as numerical instability or excessive numerical dissipation. The paper addresses this by checking for the conservation of certain quantities that were known to be conserved by the continuous equation, thereby validating the accuracy of their simulation over long integration times. This act of verification was critical. It elevated their computer output from a set of suggestive pictures to a body of credible evidence. The core of their methodological argument, therefore, is that computation is a legitimate and powerful mode of mathematical and physical exploration, appeared to traditional experimentation and theoretical deduction. This claim proved to be astoundingly influential, presaging the rise of computational science as a third pillar of scientific inquiry. Their specific work served as a premier exemplar of this new approach, showing how a machine performing arithmetic could unveil entirely new conceptual categories. Section 3. The emergence of stable pulses and the naming of the soliton. The first set of results from the numerical experiment constitutes the work's most startling and visually immediate claim. The simulation showed that the initial smooth cosine wave did behave as expected for a short time. The wavefront steepened due to the nonlinear term. However, where prior understanding suggested this might lead to the formation of a shock or a chaotic breakdown, something entirely different occurred. The paper claims that the initial wave breaks apart into a train of distinct, highly stable, pulse-like waves, each resembling a bell-shaped secant squared curve. The evidence for this is presented through a series of plots showing the wave profile at different points in time. These plots are the primary data. They reveal the birth of these pulses and their subsequent propagation. A further claim is made about the properties of these pulses. Their speed is directly proportional to their amplitude, with taller pulses moving faster than shorter ones. This was observed by tracking the position of each pulse's peak over time. The evaluation of this claim is straightforward. The visual evidence is compelling and the quantitative relationship between amplitude and speed was readily verifiable from their numerical output. Yet, the most profound intellectual act in this section is one of nomenclature. Kruskal and Zabusky recognized that these stable, propagating entities behaved with a robustness reminiscent of particles. To capture this particle-like character within a wave equation, they coined the term soliton. This was a conceptual claim of the highest order. It asserted that the fundamental excitations of this nonlinear system were discrete, localized, and persistent objects. The name itself was a piece of generative genius, encapsulating a whole new physical idea. The successful establishment of the soliton concept depended entirely on the perceived stability of the pulses in their simulation. Had the pulses dissipated or deformed over time, the particle analogy would have failed. Their data, however, showed these solitons travelling for very long times across the periodic domain, maintaining their shape and identity with remarkable fidelity. This observation of stability was the empirical bedrock upon which the entire soliton paradigm was built. Section 4, the elastic collision as a foundational principle, building directly upon the discovery of solitons. The work presents its most astonishing finding as a specific claim about their interactions. Having observed taller, faster solitons overtaking shorter, slower ones, the critical question became what happens during the collision. In a linear system, waves would simply superpose and pass through each other. In a typical non-linear system, one might expect a chaotic, inelastic collision, with the pulses being destroyed, merging, or radiating away energy. The paper's extraordinary claim is that the solitons pass through one another and emerge from the interaction completely unscathed. The shapes, amplitudes, and speeds are preserved perfectly after the collision. The evidence provided is again graphical and numerical. The author's present plots showing two solitons approaching, merging into a complex intermediate state, and then separating, having resumed their original forms. This claim of a perfectly elastic collision is what truly cements the particle-like analogy. It suggests that solitons are elementary constituents of the system's dynamics. A subtle but crucial secondary claim is also embedded here. While the solitons' shapes are invariant, their positions after the collision are shifted relative to where they would have been without the interaction. The taller soliton is pushed forward, and the shorter one is knocked backward, as phase shift is the only remnant of their encounter. The evaluation of this central claim depends on the precision of their numerical experiment. The apparent perfection of the elastic collision could have been a near miss, an artifact of limited computational accuracy. The authors acknowledged this possibility but argued the integrity of the collisions was maintained to a very high degree over numerous interactions. This specific claim had immense consequences. It pointed toward a hidden, deep mathematical structure in the KdV equation, a system that permits such perfect, elastic collisions among its nonlinear modes is exceptional. It hints at the existence of an infinite number of conserved quantities, which prevent the system from thermalizing and instead constrain its dynamics into this remarkably orderly pattern of soliton interactions. The claim of elastic collision was a direct numerical observation that screamed for a deeper theoretical explanation, a call that would be answered a few years later by the development of the inverse scattering transform. Section 5, recurrence and the connection to the Fermi Pastor-Ulam-Tsingou paradox. The final major claim of the Kruskal-Zabusky work is a grand synthesis. It connects their observations of soliton dynamics directly back to the originating puzzle of the 1955 Fermi Pastor-Ulam-Tsingou experiment. The FBUT team had observed that their simulated nonlinear lattice, when started in a low-frequency mode, did develop higher-frequency modes, but then, counter to the expectations of statistical mechanics, the energy returned almost perfectly to the initial mode. The system exhibited recurrence, a phenomenon that defied explanation. The Kruskal-Zabusky paper claims that the soliton dynamics of the KdV equation provide the mechanism for this recurrence. Their argument is as follows: the initial cosine wave analogous to the FBUT initial state breaks into a set of solitons, each with a distinct speed determined by its amplitude. Because the system is periodic, these solitons travel around the domain at different rates. Over a very long time, a moment will occur when all the solitons arrive back at their relative starting positions, having undergone a series of phase-shifting collisions. At this moment, their collective profile will approximate the initial cosine wave. The system, therefore, almost returns to its initial state. The evidence for this claim is again a long-time simulation, showing a state that is a near replica of the initial condition after a calculated recurrence time. This claim is powerful because it provides a physical picture for the abstract FBUT result. The energy in the system is locked up in the stable solitons. It cannot spread chaotically among all possible modes because the solitons are the true, stable modes of the system. The recurrence is a consequence of the coherent, particle-like motion of these energy packets. In evaluating this claim, it is important to acknowledge that the KdV equation is an approximation of the FBUT lattice. Therefore, the explanation is an analogy, albeit a deeply insightful one. The near-perfect recurrence in the KDV system provided the strongest possible argument that the F-put paradox was a manifestation of integrable, or near-integrable, dynamics, a concept that the discovery of solitons brought to the forefront of physics. The work's concluding claim is that the F-put puzzle is resolved by understanding the underlying system through the lens of solitonic, rather than thermalizing, behavior. Conclusion. In summary, the body of research culminating in the 1965 Kruskal and Zabusky paper stands as a masterwork of scientific argumentation, built upon a cascading series of well-supported claims. The initial proposition, regarding the relevance of the Korteweg-de equation, was a brilliant act of theoretical repositioning. The methodological claim for the power of computational experimentation was validated by the sheer novelty and clarity of the results it produced. The observational claims concerning the existence, stability, and amplitude speed dependence of the emergent pulses were robustly supported by the numerical data, leading to the transformative conceptual claim embodied in the term soliton. The subsequent claim of perfectly elastic, phase-shifting collisions provided the most profound evidence for the soliton's particle-like integrity and hinted at a deep, underlying mathematical order. Finally, the synthetic claim that this soliton behavior provides the mechanism for F-put recurrence offered a compelling resolution to a major paradox of modern physics. The evaluation of this work reveals a near-perfect synergy between computation, physical intuition, and conceptual innovation. Each claim builds logically upon the last, with the numerical simulations providing the evidentiary backbone for a revolutionary new way of understanding nonlinear systems. The work's enduring significance comes from the soundness of its core propositions, which opened up the vast field of soliton theory and nonlinear integrable systems, and permanently altered the relationship between theoretical physics and digital computation. It demonstrated, with irrefutable elegance, that sometimes the most complex behaviors are governed by a hidden and astonishing simplicity.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.